So thank you very much for having me. My name is Mike Wagner. I'm a product manager for ARI, and I handle mostly LED lights. And at first, I'd like to apologize that I don't speak Portuguese. Unfortunately, I only speak English, so I'll have to do this talk in English. But luckily, we have wonderful translators, so you'll all be able to understand me. So if we could put my, thank you very much. So it's a really exciting time in filmmaking right now. There's a lot of new technologies coming out. There's a lot of new ways to try things and experiment. And in lighting in particular, there's LED lighting, which is a brand new technology. It's a very exciting time to kind of experiment with all these different lights that are coming out. And we've seen a trend in film going from the traditional film of motion picture all the way to the digital cinematography that we know today. And we're seeing a similar trend in lighting, going from conventional tungsten sources to digital technology like LED lighting. And so it's interesting to see how these two technologies converge and how they play off of each other. And you know, we're seeing things for the very first time that we never had to deal with before. We're seeing things where we have to ask ourselves, really, what is white light? What does white light mean? Because with LEDs, not all white light is equal. You know, when we used to have our tungsten sources, you could have pretty much any manufacturer that you would buy, you would pretty much get the same color temperature. But now we're seeing all these different things popping up, and we have to find a way to compensate and learn how to work with them. So when LEDs first came out, we saw them in RGB, red, green, and blue. And we were able to make really neat colors, we were able to do color changes, but we really weren't able to create white light quite yet. It was much easier to create this color light than it was to create the white light. But then we fast forward a few years, and we're able to now kind of make white light, and we see it with panels. That was kind of the first major invention when it came to motion picture LED lighting in white light, was panel lighting. And that was good, and it served a purpose, and it did a great job. And we were able to light things like TV studios, and it was, the form factor was new and interesting. So we learned a lot from using panels. But as time progressed, people wanted to use LED technology in conventional sources. We wanted to be able to shape a light like you would a regular tungsten light. We wanted to cut the light and do things with the light that we had been doing for many, many years beforehand, but till a certain point we weren't really able to do with LEDs. And that's where we started to see things like LED Fresnels and LED soft lights come out into the market, and it really brought about a new way of lighting with LEDs. So we have all of these different ways of lighting, but really what we have to figure out is how all of these technologies fit together, how everything is going to work with different camera systems. So before we kind of look into the future, we kind of have to look into the past a little bit and see how light was created. So I have a neat little demo for you. So when Thomas Edison was creating the light bulb, he went through over 10,000 different ways, or tried 10,000 different ways of creating the filament that's in the light bulb. Now the filament is obviously that thin piece of wire where electricity runs through and creates resistance and creates light. So he went through many different versions. He tried beard hair, he tried cardboard, he even tried whiskers off of his cat, his poor cat. But in the end, what he settled with was sewing machine thread that was carbonized. And this was able to last long enough for him to have 100 hours of life out of the bulb. He said if he could get 100 hours, it would be a sustainable product. And so that's what he used. And to be honest, and since that time, it hasn't changed too much, the technology. We've moved to a tungsten filament, which lasts much longer. But in essence, the technology hasn't changed in over 100 years. We still run electricity through the wire, which creates resistance, which creates light, but it actually creates mostly heat. 95% of a tungsten light bulb is heat, not light. So it's a very inefficient source. So if I'm going to switch over to, so this is a spectrometer graph. So this is a live feed. I have this little wire here that's actually a fiber wire that goes down to this box on the floor, and it's giving a live feed of what light is being created. Now our eyes are very similar to the spectrometer. Our eyes are able to pick up light, and our brain interprets the light that we see into colors. In fact, color doesn't exist. It's a figment of our perception. So our brain gets these different wavelengths of light into our brain, and it processes it into color, what we perceive as color. And that's what this device is doing here. It's actually taking all of the wavelengths and it's splitting them into different wavelengths and displaying them on a graph that you see here. And you can see it's a live feed. And so humans see from about 400 nanometers to about 750, 760, depending on the individual. So that's the visible spectrum of light that we could see. There are other parts of the electromagnetic spectrum, including X-rays, gamma rays, RF frequency, microwaves, and also, of course, UV, which is ultraviolet, and IR, which is over here. Now, you can see on this side, now this spectrometer is calibrated to the visual spectrum, so it sees what our eyes are seeing. Now, if it was calibrated to the infrared spectrum, you would see a much greater spike over here, because this is where the infrared is. And remember, the light bulb gives off 95% of its energy in heat, which is over here. So, but you could see, now we've always been told that, tungsten lights in daylight are continuous spectrum sources. And what that means is that over the entire spectrum, you have some parts of light. Now, of course, this is a tungsten light, so you have more red here and less blue. But you can see there are some parts of the spectrum throughout the entire light bulb. So that was tungsten light, and we've been using that technology for 100 years. It's been great. And we moved to something a little bit different, which was fluorescence. Now, you can see that the fluorescent is quite different. There's lots of peaks and valleys, and that goes to how fluorescent light works. So in essence, there's gases inside of the fluorescent light, and when electricity is run through them, it excites and it makes actually UV light. And every fluorescent tube that you'll ever see is coated with this white powder coating. And what that is, it's a phosphor. And all of these phosphors are naturally occurring. So there's no synthetic phosphors. All of these you could find in rocks and things like that. And they put all of these phosphors in here, and they try to make a light that has enough of the right colors. So I have a few examples here of different rocks that we find and that have, actually, this is a UV light. And if I put it close, actually, if you could dim the lights a little bit in here, you'd be able to see it a little bit better. But this has green fluorescent pigment to it. And it's actually willemite from Canada. I don't know if you could see that or not. There we go. See that green fluorescent? We also have another rock. It's hackamite, another one from Canada. It fluoresces orange. You could see that one a little bit easier. We have scapolite from New Jersey. Fluoresces yellow color. And another interesting one is actually petroleum. It's mined off of the Gulf Coast of the United States, and it actually fluoresces a green color. So little did you know that all of the gasoline that you have in your car is actually a little bit phosphorescent. And so what they do is they take all of these different rocks, and they mash them up into powders. And they take all these powders, and they try to combine them to make different colors. So I have a couple of these powders here. You can imagine how fun it was getting these through Brazilian customs. But you can see they're all different colors. So these happen to be a red, a blue, and a green. But when you look at them under normal light, they're just all white. But they phosphoresce all of these different colors. So in this light here, you could see that it has a little bit of blue in it, has a lot of green in it. We're all familiar with the green spike in fluorescence. Has some red and a little bit of yellow, but it has all of these gaps in here. And that's because those are the phosphors that were left out when creating the bulb. Now, when you look at it, it looks like white light. But when you are able to dissect it and look at all the different wavelengths, you can see it's missing quite a few pieces of the spectrum. The next light I have to show is a discharge light. So we're all familiar with discharge lights. In our industry, we usually refer to them as HMIs. This is not an HMI, but it is a discharge lamp, and they're used very frequently in factories and hospitals and things like that. And you can see it's actually warming up. And we're all familiar with HMIs warming up. And what they do when they warm up, they're actually literally warming the temperature. And as they warm up, they're exciting different gases. And these different gases have different elements and phosphors in them. And as they get excited, they add different colors to the spectrum. So you can see here as it's warming up, it's quite green. You can see the big green spike here, but as it continues to warm up, it's adding more and more colors, trying to get a full spectrum as possible. Now again, this is not an HMI. An HMI has a much better spectrum than this discharge lamp does, but this gives you an idea of how this kind of technology works. You can see as it gets brighter, I have to readjust a little bit. But it's adding some yellow now. We have some spikes in blue and of course in the UV that you can see here. So you can see it looks still quite green on my hand, a very large green spike. But again, it's still warming up, it's still exciting different gases, different elements. And at a certain point, we'll actually have another version of white light. So another interesting technology. Again, a very different way of making light, but still the goal is to have enough of these different elements in here to get something that's going to be usable for us in our industry. And here you can see it's pretty much warmed up. We've got a nice piece of warm colors in here, and we're really able to now say that we could probably use this. Again, our HMIs are going to have a much better spectrum, but this gives you an example. So now we could get into the LED portion. Now I have a very simple light here. It's an RGB light. So that was the first way of making color with LEDs, was RGB, red, green, and blue. In fact, the very first LEDs that maybe you have seen were in either indicators in cars or probably on your clock radio. That 7-segmented number that you see on your clock radio, those are actually LEDs. LEDs don't have to be round, they don't have to be square. Those are actually little thin strips of LEDs, and that makes up all of the numbers on your clock radio. Now, it was easier to create a red light because basically an LED generates heat, and heat is over here. And to get the red, all they had to do was shift the spectrum over just a little bit into the red, and they had a viable light source. So that was the first LEDs that came out. Now, I'll show you. So this is, I'll show you the different colors, and I'll show them to you on the spectrometer here so you can kind of get an idea. So of course we have our red, our green, and our blue. Now, when we mix those all together, we do get a form of white light. Now, you can see that this is much cooler in color temperature than our previous light sources, but it is white light. It's creating white light. Now, again, it's missing many parts of the spectrum. You can see that we've missed almost all of the yellow. There's a dip right here in cyan, and there's only a little bit of red in here. So, again, a very primitive way of making white light, but it did work, and it worked for many years. The next one I have to show you now, there's been a lot of advancements in LEDs since they first came out. And again, the goal was always to create white light because it's what our eyes are kind of used to. The best way they found to do that was actually by using blue light and using phosphors to convert that blue light into a full spectrum source. Now this is just a light bulb that I bought at a home improvement store, and you can see it's quite bright. It's blue. And we're taking these covers, and actually let me point this at it real quick. So you can see it's mostly a blue color. It's quite bright. There we go. And this light comes with these phosphorescent caps. And you can see as I get closer, they start to fluoresce. And again, this is just taking a blue LED and putting a cover over it in order to make it white. And you can see as I put this one on how the spectrum changes. So you can see that it's really taken that blue light and converted it into a much fuller spectrum light source. And so this is pretty close. We still have some peaks and valleys, but we've gotten very, very close with this LED lighting. And you know, it's funny to see how these things progress because LEDs have been around for quite a while, but the technology continues to change. I'll go back to slides real quickly. There we go. I'll turn this off. So let's see, okay, here we go. So again, an LED, there is actually no white LED. It's always a blue LED with some kind of phosphor coating. Some manufacturers are actually painting the phosphor right onto the LED chip. Some put a dome over the LED chip, or some use it as a remote. And there's different arguments for both. Some say that the one with the remote is better for efficiency. Some say when it's painting on, it's better for an optical design. It really depends on what the lighting manufacturer is trying to do. But in essence, you have the indium gallium nitride dye, which is the blue LED, and you have some kind of phosphor coating over it, which is actually converting that blue light into a white light source. Now, there's two main methods of making white, as we had talked about. There's mixing colors, RGB. There's, of course, other ways of mixing colors. The theory is that the more colors that you have, the better your spectrum is going to be. So there's different ways of making white light, but in general, RGB is one way of making white light, of course, and the other way is the phosphor method. Now, the phosphors, of course, give a much better spectrum. So now when we talk about color metamerics mean it's the science of how colors are reproduced. Again, color is a figment of our perception, so how colors are reproduced is a study, and actually people major in this in school and try to learn what are the different ways that colors are reproduced, and specifically we're going to talk about it with LEDs. And I have some fabric here. I'm going to take a look at some different ways of making white light. I have an LED source here. It's nothing in particular, but it has 7 different color LEDs in here, and we can see all of the different ways of making white light. So here, I'll turn this on. So I'll run through these very quickly. So there's 1. There's 2. 3. 4. 5. 6, and 7. So you can see on this white fabric, all of these different colors relatively look white. They might be a little bit different. Some might look a little bit more magenta, some might look a little bit more green, but inherently they're all white. So now I have a color meter here. It's a Sekonic C500, one of the more popular ones. So we'll see what happens when we put this light meter here, or this color meter rather, and what happens how it reads the color. So this first one is about 3,000 degrees Kelvin, neutral, green, magenta. This one is about 2,900 degrees Kelvin, plus 2, green. This one is about 3,100 degrees Kelvin, plus 2, green. This is about 2,800 degrees Kelvin, neutral. This is 3,000 degrees Kelvin, neutral. This is 3,100 degrees Kelvin, neutral. And this one, again, is 3,100 degrees Kelvin plus 1, green. So according to our meter, these different ways of making white light are pretty similar. They're not too dissimilar from each other. But now, when we look at something else, if we take a colored fabric, and we look at the different ways of making white light, we could really start to see some drastic differences. So this is one way, again. I'll move out of the way for you guys. This is another way. Another way. Here's another. Here's another. And here's another. So you can see how the fabric is changing drastically. And that's because, again, whatever light is hitting this can only be reflected. So if there's no yellow in the light source that we're putting onto this fabric, the yellow is not going to be able to be able to be viewed. So let's take a little bit of a closer look here. I'm going to bring my spectrometer over and point it at the light, and we can really see what's going on there. Get tuned in. Bring it down a little bit. There we go. So the one that you're looking at right now is white and amber. So we have a white LED, so it's a phosphor-converted LED, plus an amber LED, which is, again, is a phosphor-converted LED. It's just geared towards the warmer side of things a little bit more. And you can see how we have a little bit of a dip there in cyan, but you have pretty much a full spectrum when it comes to the green, yellow, and red. Now we switch to this next one. You could see a drastic difference. Now this is red and cyan. And you could see the bump there in cyan and in red, but you have this big valley in the yellow. And that's why the yellow kind of disappears on this fabric. Again, the fabric can only reflect the light that is shined onto it. This next one is RGB, so red, green, blue, and we see the characteristic humps of the blue, green, and red. But again, we're missing some of that yellow. We're missing some of this cyan right now. So not a full spectrum. This next one is red, green, indigo. Again, you have in the indigo, in the green, and in the red. This next one is amber, cyan, and indigo. And you can see what effect that has. This is red, green, blue plus white, so that white phosphor-converted LED. And this is 5 colors plus the 2 white converted. So this is RGB, indigo, amber, and white, and cyan. And again, that gives you, it's filling in a lot of the spectrum, but you still have some dips and valleys in different places. So it's important to kind of look at those things and see what we see in our eye is not always going to be what's perceived by the camera. And now we'll kind of talk a little bit more about that. So again, this is what the human eye sees. This is, our eye sees very similar to the way that cameras see. We have different kinds of cones and rods in our eyes that see different colors. And we see blue, green, and red, just like you see here. But there's a lot of overlap, and we're only limited to the 400 to about the 760 nanometer mark. Now, there is an animal called the mantis shrimp. And this is how the mantis shrimp sees. It actually has the best vision in the animal kingdom. It could see into the UV spectrum. It could see all these different colors. It could even see into the infrared a little bit. Now, it's been guessed that the reason why it could see so well is for hunting, but also for attracting a mate. It could look at different mantis shrimps and say, oh, that one looks really attractive. If only it was that easy. So the mantis shrimp has really great vision, but of course, I don't see any mantis shrimp out in the audience, so we're going to be focusing on how humans see. So what is white light? Well, it's different. It depends on a lot of different factors. It depends on how we see things. It depends on how the camera sees things. And so this is where that intersection comes into play. How does the lighting technology interact with the camera technology? So we've looked at these different ways of making white light, and we've seen with our eye that they all relatively look white, but the camera is far less forgiving. The camera does not compensate for different white sources like our brain does. Now, I'm going to give a very simplistic view of how a camera works. I've been told that you get 10 years of bad luck for a lighting person trying to talk about camera technology to camera professionals. So believe me, this is a very simple version of how a camera works. But basically, you have these different bins, spectral bins, or pixels as we know them. And these pixels take in photons, and they convert them. The camera processes them and gives you an image. Now, if without a filter on any of these bins, they were just receiving photons, and the camera has no way of telling what color the photons of light are coming in are. So if you had this, you would have a very nice black and white image. The bins can only detect the intensity of the photon, but not the color. So in order to detect the color, we have different patterns that we put on our sensors. Now, in broadcast, you might be familiar with three sensor chips, which are actually 3 different chips that take in RGB, red, green, and blue. We're looking at what's called the Bayer pattern, which is one of the most popular ways of doing this. And basically, you put a blue, a green, and a red cover over all of these different bins, and it either reflects the color that it doesn't want out of it, or it lets the color that it does want in it. So for example, in the blue, it only lets blue in. On the green, it only lets green in. The red only lets red. And you can see there's actually double the amount of green on this pattern, and that's because our eye is more sensitive to the green channel, or the green spectrum. It's also where we get the intensity of the light from. So, and with these different bins, we're able to make a full color image. And I actually did, this is a test photography that I did. Now, the 3 images on the top are actually lit with 3 different color lights. I didn't change them at all. I didn't change them in post. I actually put red light on the one on the left, and then green light, and then blue light, and then put them into the computer and combine them all together, and you could see that we actually get a white light image. So this is kind of a practical example. You could do this yourself if you have a still camera. You could actually put a red gel in front of a light, or if you have an LED light, you could use a red LED light, and take a picture of the red, green, and the blue, and put them in Photoshop and use a blending pattern, and you'll actually get an image just like that. So it just gives you kind of a better way to understand how this technology works. So now this is an example of the spectral sensitivity of a chip. It's not any particular camera, it's just an example. But you can see that there's the blue peak, which has, it's around 450 is its peak, and the green and the red. And you can see that there's actually a little bit of overlap. And the overlap is important so that you can have that blending between colors. But you don't want too much overlap, or else you get what's called crosstalk. So it's a very fine balance between these lights. Now, when we overlay an LED light, you can see, now this is a typical, as we saw when we were using our phosphor-corrected LED here. You could see that it looks very similar. You have a spike in the blue, and then over the rest of the spectrum, it kind of evens out. But you do have this big valley right here, and that's the important part. So now, when you have this valley, now different LEDs, different white converted, phosphor-converted LEDs, this valley might change a little bit over here, a little bit over here, or even over there. And depending on where that valley is going to decide what kind of the white light looks like on camera. Now this is an example of what a tungsten light looks like with different gels over them. So you can see even when you put a gel in front of a tungsten or a full spectrum light source, you still get all of the different wavelengths of that light. It's only shifted a little bit to the color of the gel. So for example, if you put a blue gel on a tungsten light, you still have the entire spectrum going from all the way over here, and you still have some light coming out over here, but you still have the entire spectrum. With LEDs, it's quite different. LEDs are very narrow bandwidth colors. Here's an example of 2 different LED colors. You have a green and a yellow. And again, as we saw when we were doing all these different tests, they're very narrow bandwidth. It's only a certain color. You don't get the full spectrum. So now when you overlay this with the camera sensor, and this might be a little bit of an extreme example, but it gives you a sense of the problems that could occur. When you overlay them with the sensor, both of these colors, even though they're different colors and you would see that with your eye, you have a green and a yellow, the camera cannot tell the difference. The camera sees both the green and the yellow as green in this example. Now, another way of looking at this is with camera tests. So this is an important part of the process of looking at LEDs is with camera tests. And this is an example here. These 2 charts are bisected, meaning they're split in 2. The top pieces of these charts here and here are tungsten references. And the bottom is lit with a very popular LED source. And we're using 2 different cameras. These are popular broadcast cameras. We have a Sony HDC 1500 and a Grass Valley LDK 8000. And we looked at these, and you could see that there are very very big differences in some of these colors. You could see it in the grays on the bottom. You have these magenta shifts. In the yellow, you can see it's quite different. In the green, on this one as well, you could see the magenta difference down here. The yellow looks quite different. The green is different. So you can see even though it might look like white light to your eye, to the camera, it sees it very, very differently. And again, this is because of what the camera manufacturers are using. So if we go back right here to this slide here, the camera manufacturers are using those naturally occurring elements in nature to actually put these filters on the sensor. So that green and that blue and that red are all natural elements. And it varies between camera manufacturer to camera manufacturer because of the different elements that they might use, or perhaps the different processing algorithms that they're using to determine what the color is. And that's why it's very difficult when you don't have a full spectrum light to get the color that you desire or the color that it's supposed to be putting out onto the camera. So here's another example. This is with a better LED source, and you can see again it's bisected. The colors aren't as drastic of difference. You see a little bit of the red here. It's very hard to tell the difference though. And that's because this is a fuller spectrum light. There's more colors putting into this light and being mixed around in the light and putting out. So you can see how important it is to really have as much of the spectrum in that LED source as possible. So again, getting a little bit closer to our industry, closer to what we do, it's really important to see how these things react on people, on sets, because doing a color chart is a very good way of determining what colors are there and are not there. But to be able to actually see how these things look like on real life is very important. So I have this video here that I'll show you. Now this video was shot on an Alexa. We used Rec 709, and there's no color processing done. So we could see this is our base shot. It's a 650 watt airy tungsten unit. And we also used an L7C, which is our LED Fresnel. And then what we did was we compared them to other different products. So when we were setting this up, they all looked like white light. In fact, the DP and myself, we couldn't tell the difference. They all looked white, they all looked good. But we could see when we get them on camera, you could see drastic differences in the color. The chairs look different, the skin tones look different, the gray background looks different. Thank you. These are two different products now on the bottom. You can see even more drastic differences between the background colors here. The blue, this looks like blue instead of purple like it's supposed to look like. The dress looks a little bit faded. The flowers aren't quite as vibrant as they are in the reference image. So we did 3 different shots. We did a wide, we did a close-up that you can see here, or excuse me, a medium, and we also did a close-up, which will be following this. And we always shot it with the reference of tungsten, because tungsten is something that we're familiar with. We know that it produces good quality color. You can see all the colors are very vibrant. The dress looks brand new. And you can really start to see her skin tones more in this shot as well. And again, the L7, which is something that we were comparing it to, still looks very, very vibrant. The yellows are very rich. And we'll go into now the comparison shot, the 4-up shot again, and we'll really start to see a little bit more differences. If you take a look at the colors, make sure that you notice her dress, because her dress changes drastically from image to image. And of course, look at her skin tones. So you can see how this is leaning towards a little bit orange now instead of that yellow color. The dress is starting to get a little bit faded. In fact, she looks a little bit more orange or warmer. Now that could be good, and if you're making an artistic choice to make her look a little bit warmer, but if you're trying to get just plain white light and go from there, it could be not the results that you're looking for. And here you can really see, this is a really good example of how her dress, it kind of looks like old bed sheets, or like she's been, that's been through the wash cycle a few times, that dress. So, you know, again, when we were looking at these on set, to our eye, they all look good. But when we cut them and we pasted them all together and we could see them side by side, the differences are drastic. And here's that close-up shot. And this one, you could really see the difference in skin tones, in the wood over here, and this color of this rope. Always shot with the tungsten reference, of course. Here's the L7. You can see it's a very good representation of what the tungsten light was doing. And now we get into these comparison shots again. Again, here her skin looks a little bit yellow, almost jaundice. She looks a little bit ill, maybe. And in here, so this is much cooler. She looks a lot paler in here. So there's a lot of yellow in this one. So it's really important to do these tests, and that's really the best way of kind of figuring this out. Now, LEDs nowadays also have the ability to change color. And we were doing a test with the L7, the tunable white, and you could see how we could get warmer. The white balance on the camera did not change. We left the white balance as at 3200. We warmed up our L7C, and we also made it cooler, and you could see the different range that you could have. And so now, not only if you have different cameras, you could now compensate with something like with an Arri L7 or with other LED lights that are able to change the color temperature. We could also change the green and magenta point. You could see there it went magenta, and now we could go green. So you could really fine-tune the color that you're looking for to either compensate for the camera or to get an artistic result. And that's really the important thing is trying to figure out, the great thing nowadays is that we've had this technology, we're able to see the results immediately. We no longer have to wait for the film to be developed. We no longer have to hope that everything will look good. We could immediately on set with a nice monitor see what the image is going to look like and adjust and compensate and make decisions on the fly. So that's a really great thing that we're seeing nowadays, is that we're able to really make decisions much more rapidly than we were ever to before. So now that we looked at all of these different ways of making white light and all of these different ways of how the camera can see the white light, we'll talk about, well, how do we quantify what a good white light is? How do we tell what good white light is from an LED source? Now, one metric that you might be familiar with is CRI. CRI stands for Color Rendering Index. And the idea behind it is the higher the number, it's rated from 0 to 100, the higher the number, the better color rendition that you'll see on your talent or in your set or whatnot. So this example here, this particular light source, the one on the left has a CRI of 90, which is very high. You can see that her skin tones look correct. The colors are reproducing correct on the color chart. But a low CRI, you can see here a CRI of 75, she starts to look very green. The colors aren't as vibrant. The quality of the color starts to break down. But there are always different ways of tricking CRI. So CRI is by no means a foolproof method of measuring the quality of light. There are different ways of tricking it. You just could add a little bit of color here or a little bit of color there. Now, if you could see on this example here, two different images with two different lights. The one over here looks really vibrant. You can see the sushi looks fresh. The strawberries look like they were just picked today. But on the image to the right here, the strawberries look very, very old. They were shot at the same time. They look very old, though. The sushi looks kind of, I don't know if I would want to eat that. If I were to have to sit down at one of these tables and eat the food, I would probably pick the food on the left-hand side because it looks more appealing. Now, when we put the CRI numbers in here, you can actually see that this image has a lower CRI than the image on the right, which has this fruit that looks old and the sushi that doesn't look so good. So again, there's different ways of tricking CRI. So CRI was great for when you had a full spectrum source, but when we start to talk about discontinuous spectrum sources like LEDs, CRI starts to fall apart a little bit. And we can see here why. Now, CRI uses 8 different color references, and the color references are a little bit pastel. They're a little bit pale colors. You have some pale red, pale blue. There's a different standard called CQS. CQS stands for Color Quality Scale. And this is a little bit more geared towards reading discontinuous spectrum lights. It has 15 color references instead of 8, and the colors are a lot more saturated. They're a lot more vibrant. So you can see there's a strong yellow here, there's a strong red. And the other difference is so each of these different colors, when you're measuring it with a light, get a number from 0 to 100. So this might be 100, this might be 80, this might be 90. They all get different numbers. And then all those different numbers are averaged together, and you get your end result, your final CRI number. This uses a little bit different math. This is actually taking each color gets assigned a number, but they actually use something called the root mean square to actually calculate the final number. And why that is good is because you could have one number. So, for example, actually in the CRI, if all of these except for one of them was very high, let's say all of them were 90 and you had one that was maybe 50, you wouldn't get penalized as much as you would with this. Or you would, yes, that's correct. So you wouldn't get penalized as much as with the root mean square. So if one of these numbers are much lower, if the blue is way down, if it's 30 and all the rest of them are high, the overall number at the end comes down a lot more drastically than the CRI. So it's a little bit harder to trick CQS. And again, if we look at the same image, if we go back one, we look at the CQS of this, well, this makes a little bit more sense. The CQS is 93 over here, and it's 74 over there. So these are a little bit closer to what we would expect. Now, there's a lot of different ways of measuring the color of light now. There's different metrics that are coming out. People are realizing that this is an issue, and we need to find a way to measure this white light correctly so that when you guys go out into the field and you're looking at products, you could more accurately tell what is going to be a good white quality light source. This is another one that's called TLCI. And you can see now the way that they measure this one is you have a box here. The outer box is the reference. The inner box is the result of the light. And you can see drastic differences here in the red, of course, in the skin tones even, in the purple. This one with a higher TLCI has much better results. So, and this is really taking into account all of the different things with camera sensors and all of that. But again, the best way to really figure out what is going to be a good light is to do a camera test, as we did, as you saw in the video that I showed. There's all these different metrics. They're all very good. They're helpful. They're a good reference. But really, the only way to be sure about how a light is going to look onto your talent is to do a camera test and to actually put that light up, shine it onto someone's face, and see how it looks. So Plaza is a organization that kind of ratifies these standards. They ratified CRI, and they are a company that kind of tries to make sense of all of these different metrics. Now, they were mostly based in theater and live events, but they've also absorbed another company that's a US-based company that is more geared towards the broadcast. And so we're starting to see a lot more metrics coming out that are going to make it easier for us in the industry to kind of put a number, put a metric on all of these different light sources. So again, thankfully for digital cameras, we're able to see the end result right away. We're able to see what's going on and see what's happening in the camera right on a calibrated monitor, and you can make decisions from that. But because of all these different sources, we really have to be more careful. As you can see, we can't really rely on our color meters anymore. We can't really rely on our eyes, which we're so used to. We have to rely on other things, other senses. And although this talk might have raised more questions than it's given answers, hopefully it's kind of sparked some interest in you, and hopefully you'll learn a little bit more in the future. And you could really see that with LED lighting, there really is more than meets the eye. So thank you very much. If you guys have questions, please feel free to ask.
Falo em português. Quando aquela luz que você usou como referência é uma luz LED da ARRI ou é uma luz só para teste?
This is an LED fixture. So this is an LED light that has 7 different types of LEDs inside of it. And I only use this because it has so many different colors inside of it. There's lots of different ways to create white light. So there's a red, a green, a blue, an indigo, a cyan, a white, a regular white light, which I think is about 4,400 degrees Kelvin, and then an amber, which is a much warmer light. So again, this is a light that you could buy on the market. It's just one that we used in order to show different ways of making white light.
Okay. Because when you put it on, you have a lot of fringes, and because you have many sources, different sources. So.
Correct. Yeah, I mean, you could add more diffusion to this if you wanted to in order to to get a more even beam. But again, this is just an example. There are many different types of LED lights out there.
Okay.
Olá, meu nome é Luiz. Hello. All right, translation. Minha pergunta eu uso muito o CRI para saber se eu gosto de usar o Fresnel de tungstênio. Então, quando alguém fala em LED, eu penso, poxa, mas o CRI é muito baixo, não chega ao tungstênio. Eu posso começar, a partir de agora, a pensar mais no sensor da câmera do que no tungstênio em si? Não, esse sensor ele funciona muito melhor com LED, ou, aliás, pode dar a mesma resposta com LED do que com o tungstênio. Eu já posso dizer isso, que tem algum sensor que would be the...
Well, so tungsten is a full spectrum source. So when you have a full spectrum source, it's easier to go from different camera manufacturer to different camera manufacturer. Because it has all of that different color, the different wavelengths of color, you don't really have to worry about, well, what will it look like on this camera or this camera, because it has all of that different wavelengths of color. Now, when you have an LED, which only has selected pieces of color in it, it becomes a little bit more difficult. You kind of have to rely on, so for example, if you use a red camera, an LED light might look different than on an Arri camera. And this is because the sensors are actually made differently. It's a different camera, it's a different sensor. The elements that they are putting on the sensor to do the Bayer pattern are different. So different colors, even though they might look the same to your eye, might look very differently on different cameras. And so that's the challenge nowadays. So when we had much fewer variables before. You had film, and you either had a daylight or a tungsten film stock, and then you had tungsten or HMI lighting or maybe fluorescent lighting. But now we have different LEDs. So the interesting thing is that LED manufacturers are now the light bulb manufacturers, meaning that before, when you used to buy an Arri light or maybe you buy someone else's light, you would always assume that you would get the same color out of it because you would be using pretty much the same light bulb. Even if there were different manufacturers of light bulbs, the color would pretty much be the same. It's using the same technology. But with LED lighting, manufacturers are now able to customize the spectrum that's coming out of that light source. So everyone that's making their own LED light is also making the actual light bulb. And so that's very different from what we're used to. And that's what is kind of creating all of these different challenges.
Well, firstly, thank you for the great speech. And one of the things that you didn't quite say is the cost of the technology. Because a lot of us is like getting off the school and trying to build a portfolio. And cost is a great thing for us. Mm-hmm. So how do you see the technology in terms of cost? Because I can go to the store, get a 300 watts bulb, and start producing things. Mm-hmm. What about the cost of the technology of the LED lighting?
Yeah. Well, certainly because it's new technology, it's definitely more expensive than the older technology. So of course, that's always the factor. You know, the thing to keep in mind is that there are many benefits to LEDs. There are, of course, cost savings when it comes to electricity, when it comes to the heat output. So if you're working in a smaller space, the heat. So there's all these different benefits that's associated with LEDs. And that's really what you have to look for. What I kind of see it as is, right now, this is a great time to be in filmmaking. We have all of these different tools at our disposal. And depending on what we're doing, depending on what the project is, depending on what we're shooting, we could pick from these tools and choose the ones that we need for that particular project. So for example, if you are shooting something that it has to be very mobile, maybe you're trekking through the forest and you have to shoot at night, it might be there's no way to bring a generator into that scenario. The only way to do it might be through battery-powered lights. And the most efficient battery-powered lights right now are LED lights. So if you need to have some kind of a portable light in there, the LED might be the best technology for you. So I think over time, to go back to your question a little bit, over time the cost will definitely come down, just like we saw with HMI technology and just like we saw with fluorescent technology. The cost will come down, I don't know when that will be, when that time where the tungsten cost and the LED cost kind of intersect and you get the same brightness, but it's probably several years away before we see the equivalent costs. But you know, it's just about weighing the different pros and cons, I guess, of the light. You know, with a tungsten light, it's going to consume more energy, it's going to be hotter, you're going to need to probably have a lot more power, so maybe a generator. But with LED light, you're going to have something that's cool to the touch, cool on the talent, going to take a lot less power, all of these different factors. So.
Okay, the second part of the question is about the high output light. Like if you are shooting high speed, you need a lot of light. How does the LED technology meet these specifications?
Yeah. Well, there are many light sources out there that can work in high frame rates. It's all a matter of if they produce enough light in order to do that. Again, of course, it depends on how many frames per second that you're shooting on. Many people, if they're shooting outside and they need to do high-speed photography, a lot of them still rely on HMI technology and high-speed ballasts. If you're doing something inside and maybe you don't need as much light, there are definitely LED sources out there that can do high frame rate photography. And so it's definitely a good option because you're not putting as much heat onto the subject anymore. So if you're doing something like, you know, an ice cream falling into a bowl or something like that, you could actually use real ice cream now and use LED lights and not have it melt within a fraction of a second. So it's definitely a benefit. You can do it. Not all LEDs can do high frame rate photography. It depends on the electronics inside of the light. So it's really finding out the specifications of that particular LED light and making sure that it's going to be able to work at that frame rate that you're shooting at. Yep.
Hi, my name is Kyle. I'm a camera assistant. And basically, all I want to know is sell me the array. LED, because what is the main benefit I'm getting from your product that I don't get from the Chinese products?
Well, since you asked, I could definitely answer that.
Thank you.
Since you asked. So, you know, when we were developing our LED light, we have two LED lights actually, which is the L7C, which is our LED for now, and we have our Lowcaster, which is a smaller soft source. So I'll talk about the L7 first. So when we were designing the L7, our primary goal was to create the best color rendition and the best quality of light that we could. We wanted to make sure that the light coming out of that light could mimic as closely as possible to the conventional sources people were used to as possible. We wanted to make sure that the edges of the beam were correct and that the field of the light was even, and that you could focus it just like you would with a regular light, and you could cut the light just like you would with a regular light, with barn doors or with flags. So that was our primary goal, and we put a lot of research and design into figuring out how to do that. We use an RL7C, which is our color version. We actually use 3 different kinds of LEDs. We use RGB and a white light. And from that, we're able to create any color temperature from 2800 degrees Kelvin all the way up to 10,000 degrees Kelvin. Plus, we could have the ability to tune the green magenta point from full minus green to full plus green. In addition to that, we're able to put it into a color mode and make whatever kind of, I use the term party color, any kind of color that you want in the spectrum, and also change the saturation of that color. So it's an extremely flexible light. It's very, very bright as well. It's about the equivalent of a 650-watt light. So for most people, they say that that's bright enough, especially for the digital photography that they're doing nowadays. But you know, again, it's really, when it comes down to it, when we say, well, what's the difference between ARRI and brand X? It's the quality of the light and the quality of the product itself. It's a robust light. We know how all of you work. We know how all of you use lights and how they get thrown into the back of the truck at the end of the day. So it's a very robust light, and we wanted to make sure that that was a priority. And it's versatile. You know, there's not a lot of LED lights out there that have the tunability that we kind of strive for. Now, a lot of people are focusing on white light, so either a tungsten or a daylight source. Our key feature is that we're able to do tunability. So you could change the mood of the scene simply by turning the dial on the side of the panel. And if you'd like a demo, so we have an L7 at the ARRI booth, and we could take a look at it. You could come by. I'll give you guys a demo if you'd like. But it really is a fantastic light source.
Bom dia. A minha pergunta é a seguinte: ao longo dos anos eu vi muitas mudanças de tecnologia de iluminação, de produção de luz, né? A gente usa a luz, qualquer que seja, para captar a imagem, né? Então, do arco para o tungstênio, do tungstênio para fluorescente, houve a evolução da fluorescente, aí agora estamos entrando no LED, e tem outras tecnologias que também estão chegando. Você tem algum conhecimento dessas novas tecnologias, como plasma, polímeros, coisas desse tipo? Porque, assim, em 20 anos, a fluorescente compacta já não existe mais. As dicróicas já não existem, acabaram. Então, a minha pergunta é, o LED vai ser uma tecnologia que vai ficar ou vai ser ultrapassado por outras mais eficientes ainda?
Well, you know, the best way to answer that question is that it's up to you guys what stays and what goes away. You know, if the technology is going to, if you find the technology helps you do the creative work that you do, that's when the technology stays. So for example, when fluorescence, when Kinoflow came out with their product, they really made fluorescence a viable product for us to use in our industry. Before, we had to make weird things with fluorescence, we had to make strange reflectors, and the color wasn't so good, but someone from Kinoflow took those bulbs and made them the color really good in a form factor that we could use in our industry. I do think that LEDs are going to be around for quite a while. They're very flexible. Of course, there are new technologies. You mentioned plasma. It's yet to be seen what happens with plasma. You know, there are definitely disadvantages, but there are definitely advantages to it. So it really remains to be seen, and I think it's the market that really drives that. And in fact, ARRI is very keen on listening to customers and seeing what they like and what they don't like. I think that the fact that you can tune an LED light, the fact that you could tune the color, that is really what's going to change things a little bit, because before, you didn't have that versatility. You didn't have the ability to do things as quickly as you can with LEDs. You either had to change a gel out, you had to, you know, if the light was up high, you had to go up high and put a different gel in if you wanted to change it. But now you could use DMX and you could control everything from a lighting console or from a computer or from an iPad. So it's that kind of technology that I think is really exciting. I hope that answers your question.
Eu estava querendo falar num sentido mais amplo, porque a gente está no mundo real, né? A gente não trabalha só em estúdio, né? E o mundo real, na verdade, você tem uma mistura muito grande de fontes luminosas de todos os tipos. Você vai em qualquer lugar, você tem 5 tipos diferentes de temperatura de cor. E aí acrescenta-se o LED, que tem uma temperatura de cor diferente, aí tem uma outra tecnologia que está surgindo, e tem outras coisas. A minha pergunta era um pouco mais ampla do que isso, mas a resposta é satisfatória. No caso do estúdio, eu acho que é uma coisa assim, eu acho que é bem interessante a resposta que você deu, eu acho que é satisfatória.
Welcome.
Alguém quer fazer mais perguntas?
No? Well, thank you all for coming. Oh, we have one more question. Lifetime? So it depends on the manufacturer, but most manufacturers say about 50,000 hours. So again, it depends on how they're cooling the LEDs, on what LEDs that they're using. Most manufacturers say around 50,000. It could go as low as 20,000 hours and maybe up to 70,000 hours. It really depends on the fixture. But a very long time, much longer than any of our conventional sources that we're used to. I mean, most HMI bulbs last for maybe 300 hours, or, you know, tungsten light bulbs only a little bit more. So again, it depends on the manufacturer. It depends on the manufacturer. Most of the time, my guess would be that you'd have to send it back to the factory to repair it. Some people have light engines that are replaceable, but it really, again, it depends on manufacturer to manufacturer. Any other questions? Yes.
Desculpa aí, pessoal. Eu vou falar I'll speak in Portuguese.
Sure.
Vou falar em português, tá? Eu queria só uma ideia, como é que se compara as luminárias de LED da ARRI em termos de comparar com o Fresnel, comparar com os potes abertos, convencionais, como é que é essa comparação hoje? Por exemplo, eu posso pegar uma luminária da ARRI e ela funcionar como um Fresnel mesmo, com lentes e lâmpadas de quartzo halogênio, ou é diferente, ou como é que é?
Well, again, it kind of depends on the manufacturer. So, I mean, when we talk about the L7, it mimics Fresnel light very well. If you have someone else, some people don't use Fresnel lenses. For example, this light here is not a Fresnel fixture. It's simply made to wash color or light onto a surface. So that's really the goal of this light. It really depends on the goal. There's other Fresnel lights out there, of course, as well. We're not the only one. There's other manufacturers out there that make Fresnel lights. It's kind of a little bit maybe subjective of how good other ones are. We think we're the best, and we could show you. We do a lot of tests ourselves. We make sure that we're the best. But it really is kind of, it depends on the manufacturer, what they're trying to do with the light. Some people just want to throw a lot of light out there at once and not worry about the beam field. They just want to get out a lot of light. If you take a panel, for example, that is just trying to get enough light out for a certain distance. So Fresnel lights are definitely, it seems to be the way things are going. People want, I think you guys all want to be able to shape the light and do things with the light that you did in the past with conventional sources. And so that's the aim of a lot of companies, including ARRI. We want to make lights that you guys are able to be creative with, and you don't have to make sacrifices because of the technology. You want to be able to have all the tools that you need to in order to make the kinds of images that you're looking for.
Thanks.
Is that as far as how much light LEDs can put out? This one you showed is equivalent to about 650 watts for now, more or less. But will we start seeing like 2,000 watts, 5,000 LEDs replacing these bigger lights? I
think you will. I think it's LEDs are still, especially in our industry, LEDs are still at the beginning stage. They're still, I think they've been in our industry for maybe about 6 years, which is still pretty young. And you could see there's definitely been a progression. As we saw with the different slides that I had, we started with panels and moved to different kinds of form factors and interesting ways of creating the LED light. So I think it's just a matter of time. The LEDs continue to advance and continue to develop every day. Of course, LED lights are not only used in our industry, they're used in general lighting as well. And there's a lot of research being done in how to make LEDs brighter, more efficient, better color. So I think it's really only a matter of time. I don't know what the timeline is going to be, but I think that we'll definitely start to see brighter fixtures out there in the market.
Desculpe, eu tive que sair, mas eu não sei se você mostrou como é que se controla a cor naquele aparelho. Como é DMX, IMX? Mas como que você controla a cor lá? Como é que você muda isso?
Well, it's in this particular light, you're able to just mix the different channels of LEDs in order to find the light that you're looking for. Again, it really depends on the manufacturer. We just use this as an example, but there are 7 different LEDs in here, and it's just a matter of changing the intensity. I think that this company might offer presets, so if you're looking for 3200 or...
Não, eu entendo isso, eu estou dizendo, mas você controla do iPad, como é esse controle daqui para lá? Wi-Fi?
Yeah. So there's a lot of different ways of controlling it. I'm actually using DMX here, and what's happening is that I have a DMX cable running to this little box over here, and this box is connected to a router, and the router is generating a Wi-Fi signal, and the iPad is connected to the Wi-Fi signal.
Ok, e você pode controlar ele individualmente, ou seja, com o teu iPad você pode então localizar o refletor numericamente e controlar por com o iPad. Verdade?
Sure, yeah, it works just like regular DMX. So every light has a channel, and so if you address this one as 1, And then I think this light has, I believe it's 8 or 9 channels, so the colors plus intensity. You could do individual channels. Now, if you have a bunch of these, or a bunch of any light, bunch of L7s, you put them all to the same address. You could change everything at the same time, or you could give them all different addresses. So it's definitely a new way of controlling lights that of course, you never have to deal with tungsten lights. It's just you put on the switch and it's on. With a lot of this, they really are digital lights. And so it's kind of a digital light. We have digital cameras and digital lights now. And with these digital lights, you could do a lot more. So if you had a very big rig, if you were doing a very big show and you had lots of LED lights, L7s, these, whatever you might have up in the rig, you could address them all individually, you could address them all same, and you could have individual control of every single light. So there's a lot of power in that, and being able to control it from something like an iPad. You have a lot of control and power over that. It's just a matter of kind of learning it, and it could get a little bit complicated. I think that, it's funny. We've gotten much more complicated in our lighting, and we've made things harder for ourselves for the sake of convenience, I think. So it's interesting to see if you can learn the technology and learn how everything kind of interacts with each other. You could have a much better grasp of it, and you could control it, and it could really become an advantage. If you don't know it, it could become a burden. So it's just a matter of kind of getting familiar with it. And this is just one way. There are many other ways. You could use a computer. You could use a lighting console. So you could, if you want to have something that's a physical fader, you could do it that way as well. So there's a lot of different options.
Mas é mais fácil do que o método do dimmer, não é? Porque antes você teria o dimmer em cada canal, mas você tem o dimmer num container. Então aí você tem somente o cabo da power cable, né? E o controller. O que é o controller? É uma caixinha.
Yeah.
Can you show me? Então você teria desses por refletor, por unidade.
No, one per however many. So this is just, all that this is doing is converting DMX into a signal that the Wi-Fi could pick up. So they call it a node, I think. And there's different companies that make them, but yeah, there's no longer do you need a 1-for-1 dimmer. That big dimmer that you used to have, you don't need that anymore. Most of these have onboard dimming and controls. So what this is simply, I have a power cable, and the power is, it's just giving it electricity, and then the DMX cable goes right into this little box.
Okay.
And
so essa caixa pode receber múltiplos refletores.
Correct.
E você controla isso digitalmente por Wi-Fi. Então é muito mais fácil que a tecnologia do dimmer antigo.
Yeah, I think so. Yeah.
Obrigado.
Yeah. Mm-hmm.
Você pode variar a potência da luz sem mudar a temperatura de cor escolhida?
The light power without changing the color. You mean the intensity?
Yes.
Yes. You can change the intensity. Mostly, again, it really depends on the fixture, but mostly with LEDs, with RL7 certainly, you could leave it on 3200 degrees Kelvin and dim the light, and there's no color temperature change. And that is because we've put a lot of very complicated algorithms into our software that enables you to do that. So the computer, there's basically a very small computer inside of an L7, which is saying, okay, as you turn the dial, it's changing either the intensity or the color temperature and keeping things constant or changing it. So a lot of it is, again, it depends on fixture to fixture. I could tell you from our standpoint that the L7 does do that. There are other lights that I know can as well, but it really is talking to the manufacturer and finding out what the specifications are.
Mais uma última pergunta. O LED é uma luz pulsante, né? O LED é uma luz contínua ou é uma luz que tem um flicker com a frequência da rede?
If I think I understand you correctly, you mean, is it one? Is it alternating?
Por exemplo, a luz fluorescente, ela pulsa, né? Dependendo da frequência da rede, 60 vezes por segundo, ela pulsa, acende, apaga, acende, apaga. O LED também, ou ele é constante?
No, they pulse as well, but it's extremely fast. And again, it depends on the manufacturer, but some have different frequencies. But usually it's a square wave method, but it's very, very fast. You can have it faster than a tungsten bulb, you can have it faster than an HMI. It really depends on the frequency that the electronics are pushing the LEDs.
Por exemplo, da ARRI, qual é a frequência de pulsação?
Well, that's actually proprietary information. A lot of that we don't share with customers because it's kind of part of the design of the light. So a lot of that is not given out as public information.
Mas não é uma coisa que você perceba mudando a velocidade, por exemplo, do obturador, não acontece nada. É como se fosse constante, é isso?
Correct, yeah. And again, there's limitations just like anything. So there's limitations in terms of the frame rate. We have different frame rates that we could go up to. Other manufacturers have different frame rates. I've seen some LED lights that could go up to 10,000 frames per second. Some could go only up to maybe 120 or 60. Some could go to 500. So it depends on, again, it's all depending on how they design the electronics. Because it's an electronic light, it's all in how they do the electronic design. So it's different for every light, but for the most part, if you're changing your frame rate, maybe within 120 frames per second, most LED lights are going to be fine. Again, the best advice I could give to anyone is to do camera tests. Always do camera tests, especially if it's something that you haven't used before, whether it's to see if there's going to be flicker or whether it's to see what the color is going to look at. The only way to be positive is to do a camera test.
Thank you.
Well, again, thank you very much for coming. I really appreciate your time. If you have more questions, if you're too shy to ask them in front of all these people, come up to me, come on and ask questions. I'll be at the ARRI booth. I could give you guys a demo as well. So again, thank you very much.